How's it going, guys, and welcome back to video 2 of module 10, gases. My name is Brock Grant, and today we're going to go through a few of these questions and help you out with your studies. So prerequisites for this module, obviously checking out video 1 of this series, so you have an idea of the gases, formulas, and the properties in which they work with. So we're going to be going through a fair few questions. Again, don't forget to click the annotation if you want to fast forward through this video, so you don't have to click through the little timeline there. Okay, so let's get started. So let's check out page 246, question 6. So a sample of gas has a volume of 635 ml at 722 torr. So at a constant temperature, what will be the new volume when the pressure changes? So a couple of things are jumping out at me here. One, we are given a volume and we are given a pressure. And it's saying at a constant temperature, what will the new volume be? Okay, so we are seeing pressure, volume, and a change to volume. So this should spark to mind Boyle's law. So Boyle's law is P1 V1 is equal to P2 V2. Now, let's run under the assumption that you forgot this, okay? Let's say that you're in the exam, you have a total mind blank and you go, crap, I can't remember what it is. What you can do is, we can use our ideal gas law. So if you're going to memorize any equation, make it the ideal gas law. So we'll go PV equals nRT. So let's have a look at this question. So is pressure mentioned? Yes, so pressure is here. Is volume mentioned? Yes, here we go. Is moles mentioned? No. Is the constant mentioned, or do we need the constant? No. Is temperature mentioned? Yes, but it said at a constant temperature, so that means it's not changing. So that means we don't need any of those three. So I can just delete those. And look at that, here is Boyle's law. So P1 V1 is equal to P2 V2. So the first thing we need to do here is we need to look at our torrs, okay? We need to convert it. So we should have memorized that 1 atmosphere is equal to 760 torr. Now this is where we use our conversions. So we go given times desired over given is equal to desired. Now we are given torrs, so we're going to go 722 torrs multiplied by the desired. So what do we want it in? We want it in atmospheres over given. So we're given torr, and we know that 1 atmosphere is the same as 760 torr. So to convert this, we go 722 multiplied by 1, which is 722, divided by 760. And that will give us 0.95 atmospheres. So that is what our torrs are up here. So we go 0.95 ATM. So now is when we can use our Boyle's law. So we want to know what the new volume will be. So I'm going to rearrange this so that volume is by itself. So we move the P over. So remembering this is a times, so that's going to turn into a divide. So we're going to have P1 V1 over P2 is equal to V2. So that means that our first pressure, our initial pressure, is 0.95 atmospheres multiplied by volume 1, which is 635. Now, it's okay for this to stay as milliliters as long as we keep it constant. So we have 0.95 atmospheres times 635 milliliters divided by 2.5 atmospheres, which means our V2 is going to equal, if we punch that into the calculator, 241.3 milliliters. And that is our new volume. So that's what it's going to change to. Okay, now let's move on to part B. So again, we're looking at it's the same type of problem. So we're going to be using P1V1 is equal to P2V2. The only thing that's changed is that now we've got, instead of atmospheres, we've got millimeters of mercury. However, because we had already converted this to 0.95 atm, and because atmospheres are a part of our standard temperature and pressure, it's a good thing to just convert it back to atmospheres. That's what I personally do. Again, it's your option. You can choose to do what you like. However, I personally will convert everything to atmospheres. So 795 millimeters of mercury. So I know that 760 millimeters of mercury will go into 1 atmosphere. So it's the same deal. We go given times desired over given equals desired. So we have 795 millimeters of mercury times desired, so we want it in atmospheres, over given, which is millimeters of mercury, 1 atmosphere for 760 millimeters of mercury, and that will give us 1.05 atmospheres. So now we can compare our two different variables here and see what the new volume will be. So P1 will be 0.95 atmospheres times the volume, which is 635 mil. So again, we're going to move this pressure over like we did before, divided by 1.05 atmospheres will equal V2. So the second volume will be 0.95 times 635 divided by 1.05, and that will give us 576.7 milliliters. Okay, now let us look at page 246, question 16. So a 2.5 litre sample of sulfur trioxide is at 19 degrees at 1.5 atmospheres. What will be the new temperature in degrees Celsius? So I'm going to put a big square around that. If the volume changes to 1.5 litres and the pressure to 765 torr. Okay, so we're seeing that we have a volume, we have a temperature, and we have a pressure. So as soon as I see 3 different types of variables here, I'm going to jump straight to the ideal gas law. So that is P1 V1 over T1 is equal to P2 V2 over T2. Okay, so now what we do is I'm looking at my units here. So we want the temperature in degrees Celsius, but we have our temperature in degrees Celsius over here. But whenever we are using a temperature in these formulas, yes, it does want it in Celsius, we still need to convert it to degrees Kelvin. So we need to, first of all, convert our degrees Celsius. So we have 0 degrees Celsius goes to 273 degrees Kelvin. I'm also seeing here that we have our pressures, they're different. So we're going to have to convert our torrs to atmospheres. So we know that there is 760 torr that goes into 1 atmosphere. And we look at the volume change, and they're both in liters. So the volume's fine. So first of all, we need to change our units. So we have 19 degrees. So what we're going to do now is we're going to go 273 plus 19. And that will give us 292 degrees Kelvin. So we know our T1. So we know our T1 is 292 degrees Kelvin. So that's awesome. We've got this one done and dusted. The next thing I'm going to do is I'm going to look at my new pressure here. So 760 torrs is equal to 1 atmosphere. So I'm going to go given, which is 765 torr times desired atmospheres over given torr. So 1 atmosphere, 760 torrs. And that's going to give us 765 times 1 divided by 760, a P2 of 1.007 atmospheres. So over here, I'm just going to write P2 is equal to 1.007. Okay, so what we do now is, now that we've made sure that our units are nice and converted, we do what's called a plug and chug. We plug all of our numbers into the equation and we chug out the number. So P1 is 1.5 atmospheres times V1, which is 2.5, divided by T1, which is 292 degrees Kelvin, is equal to P2. So P2 we've got over here is 1.007 atmospheres times V2, which is 1.5 liters, divided by T2, which we don't know, so T2. Now, what we can do here is we can start to simplify. So we can go 1.5 times 2.5 divided by 292, and that's going to give us 0.0128 is equal to, so this is where we can simplify this. So we've got 1.007 times 1.5, which will give us 1.51 divided by T2. So we can rearrange these two here. So that will give us T2 is equal to 1.51 divided by 0.0128, which means that our final temperature, T2, is equal to 118 degrees Kelvin. But the question asks for it in Celsius. So what we do is we go 118 minus 273, which will give us our degrees in Celsius, and that will give us a total of negative 155 degrees Celsius. And that is our final answer. Okay, moving on now to page 246, question 24. So, how many moles of nitrogen will occupy a volume of 3.5 liters at STP? Now, big thing here that's immediately jumping out at me is STP. So that means that you should be instantly writing down PVNT. Pressure 1 atmosphere, volume 22.4 liters, 1 mole, and temperature 273 degrees Kelvin. Okay, straight away, that should jump into your mind like that, as well as the equation PV equals nRT. So, what I'm going to do is, how many moles of nitrogen? So, moles, we don't know, will occupy a volume of 3.5. So these variables are being changed. So 3.5 liters, but the rest are at STP. So what I'm going to do is I just straight away use my ideal gas formula. So we have PV equals nRT. So what I'm going to do now, just to stop confusion later on down the track, is I'm going to rearrange our formula here so that we have already isolated the key variable that we want to find out. And in this case, it's moles. So what I'm going to do is, so we have moles and the constant. So remembering that the constant is 0.0821. So this is a multiply. So if I move this over, it turns to a divide. And the operation with temperature is a multiply, so that's also going to turn into a divide, meaning that by rearranging this equation here, we will have PV over RT is equal to moles. So now it's plug and chug. So that means we just plug in the values, chug out an answer. So moles is equal to pressure, which is 1 atmosphere, times 3.5 liters, divided by 0.0821 times 273. So that means that moles is going to equal to 0.156 moles of nitrogen. And that's it. That one's a nice easy one. So whenever you see that term STP, instantly this and this should be popping straight into your mind. Okay, so question 44. In the lab, a student or students generated and collected oxygen gas according to the following equation. So down here, how many mil of oxygen gas at STP were generated from 50 grams of H2O2? Okay, so instantly STP, we've got the ideal gas law coming into our minds. We've got our standard temperature and pressure values popping into our minds. But what's also catching my attention is the fact that we have a mass. So I'd say, well, hang on, mass isn't in any of these formulas, so how do we use it? And the connection is moles. So what we do is we go, so our first step is moles is equal to mass over molar mass. Because remembering that you'll be given a periodic table in all of your examinations. So moles is equal to mass, which is 50 grams, divided by the molar mass, which is 16 times 2 plus 2, which is going to be 34 grams per mole, which means that moles is going to equal to 1.47 moles. So the big thing here too is that it's asking how many mils of oxygen gas are going to be generated, and that's fine, but we are given the mass of H2O2. So this is when our old stoichiometry friend comes into play. So what we need to do is we need to divide our moles by 2, because we've got a coefficient at the front here. That will give us a mole of 0.735 moles, and we carry this over. So that means that the moles of O2 gas is 0.735. So now that we have our particular amount of moles, we can now use PV nRT. So the question is asking for volume. So I'm going to rearrange our formula to have volume by itself. So we just move our pressure over. So it's going to be volume is equal to moles times constant times temperature divided by pressure. So that means we're going to have 0.735 times 0.0821 times 273 divided by 1, and that will give us our final volume. So all we need to do is multiply all of this through, so 0.735 times 0.0821 times 273, and we're going to get 16.37 liters. Don't forget, remember our units for STP, our units for the ideal gas law. Volume is in liters. So it means in order to convert this into milliliters, we need to multiply by 1,000, which it means that we're going to get 1.6 times 10 to the 4. And that is our answer in milliliters. So let us know.